Hi, my name is John Warner, and I'm honored to be asked to spend some time and share some thoughts with you about green chemistry and sustainability. I currently work for a company called Zymergen, which is a company that's trying to invent materials from fermentation tanks and microbial processes to invent products, all across all the human experiences. I can't help but smile at the two logos for the space station and for Zymergen. You can see that I can't help but see how they can actually go together. It's a little fun there. All right. Sustainability, the confusing concept to a lot of people. And the reason for that is myriad, and I'm not going to go into the politics and the history of confusion around sustainability, other than to say the following. One of the issues is that when we estimate the sustainability of material or a process, we must really be careful to choose the right boundary conditions that define the system. When we look through history and we see all the different controversies and things, what ends up happening is different conclusions and subsequent controversy will be created depending on those boundary conditions, right? Paper or plastic? Well, it depends on how you define the system, which is more sustainable. Glass or cans? Well, it depends on how you define the system. So we end up, there's a certain amount of subjectivity, and it is the subjectivity that ends up creating the controversy and why sometimes we just can't get out of our own way. All right. And so the different boundary conditions lead to different conclusions, and I feel a lot of confusion. So when I was asked to speak with you about the space station and sustainability, I jumped out of my seat because for me, when I think of the International Space Station, there's no ambiguity about boundary conditions. All right. So in a way, the high-tech science innovation perfect laboratory is also a perfect laboratory for sustainability, because inputs and outputs have a very different and also well-defined meaning on the space station that on Earth we don't have. And so, yes, there's high-tech, amazing opportunities to invent and innovate, but taking in the other framework and realizing that the space station, because of all the planning that is required, because of all the balanced equilibria that we have to maintain, it's also the ideal framework for sustainability. And the world needs that right now. So when we try to talk about sustainability, we find, oh, there's a book on cradle to cradle, there's resilience, there's natural capitalism, there's circular economy, responsible care, limits to growth, biomimicry, the UN SDGs, the European Green Deal, the Alliance to End Plastic Waste, green chemistry. There's so many approaches. What's super important to me is to recognize that all of these approaches have merit. It's not like one of them is like, I become very sad when someone says this is the correct way and this is an incorrect way. We have a diverse set of problems. We humans are a diverse set of people. If one of these methods speak to an individual and give them reason to work forward towards a sustainable future, then great. That's a wonderful thing. So I am never going to say one is better than the other or one is correct and one is incorrect. We need to realize that we need all of these approaches for us to truly create a sustainable future. So instead of looking at which is better, maybe what we should be doing is looking at how do they all fit together. And that requires us to agree on a certain framework of when we talk about materials on Earth. What are we talking about? Okay, so the way I look at it is one cycle that we focus on is the use and reuse cycle, where products, we want to keep them in use and reuse as much as possible. All right. Hermit crab gets bigger, leaves its shell and goes to another shell. That shell was always there. It didn't create it. It's using it and reusing it. Okay. In the human built world, we make car parts, playground parts. We don't expect these things to last for a day. We want them to be durable goods to last as long as possible. And we have reusable products that we expect to use over and over again. The hallmark of this system is that we're trying to conserve the composition and the form. We expect the chemistry to remain unchanged and the shape to remain unchanged for this to work. Of course, we know there's this thing called entropy, and inevitably something's going to go wrong. When that something happens, we need to go to the next system in my structure here, the recycle system. Now, the recycle system takes materials and components, manufactures the products, and then takes those products and mechanically recycles them back to the materials and components. And this system can be sustainable, and we can continue this. In the natural world, I would say that a bird finds a twig and builds a nest. A beaver cuts down a tree to make a dam. We, in the human-built world, we collect waste plastics, we sort them and shred them and melt them and granulate them so that we can use and reuse through recycled plastics. In this system, it's different than the previous system. And now we do want to conserve the chemistry composition, but we do allow the form to change. The shape of the stuff can change. And that's the difference between the previous cycle, the use and reuse cycle, and the recycle system, is that recycle system, we hold the chemical composition constant. But of course, entropy again, the polymer chains, the paper fibers, the metal structures, every time we recycle things, a little bit of chemistry does happen. We break the chains, we break the fibers. And so we can only mechanically recycle so long until we lose those physical and mechanical properties. That has us then go to the next system. This is my favorite, the next system, what I call the materials metabolism. Here we take the molecules and the ingredients, we synthesize materials and components, and when those materials and components have problems, we go down and we molecularly reprocess. This isn't necessarily exactly the same thing as chemical recycling. That's a little part of it, but it's a much bigger concept than that. Okay, and so here's a picture of my wife and daughter, and it's a very old picture. My daughter is now 9 years old. But what happens when we eat? When biological organisms eat, we take large molecules and we break them down into small molecules, right? Carbohydrates go to sugars, proteins go to amino acids, lipids go to fatty acids, but that's not all. At exactly the same time that we're breaking down these things, we're eating food and we're breaking it down, at exactly the same time, we're growing hair, we're growing fingernails, we're growing blood cells. Nature combines at the same time catabolism and anabolism, the forming back of the big molecules, and together that's called metabolism. I look at this, I say, humans, we haven't even begun to think about how to do this realistically. Okay, when you think of the energetics that are involved, biology has evolved with this ATP molecule that facilitates to allow this energy to happen, but we don't do that. Think about it. In the human-built world, we may make a material and then we warehouse it, we ship it somewhere. And then when we deconstruct it, we separate it, we purify it, we put some of this, everything is temporally and physically displaced. Okay, that we will have ingredients, ship them to some other place, make a product, then deconstruct that product, and everything is about separating and purifying, whereas in nature, everything happens at the same time. If the natural digestive system was invented by humans, we would only have proteins for breakfast, carbohydrates for lunch, and lipids for dinner, because heaven forbid we can't mix them. We don't have a process to mix them. 3.8 billion years of biology evolution has shown that, yes, we can separate and mix them. And that, to me, is the vision for the future. I imagine a world where we can have what I call the materials metabolism, where we, in synchronicity, have orthogonal chemical reactions that can happen in the same time in the same space, so that disassembly and reassembly can happen. And why this is so possible and why I'm so optimistic is because now there's no rules. We're altering composition and the form. We can do whatever we want in this system. All right. And so this what excites me. Then if we come back down the entropy tree to the natural world, we take these molecules, ingredients came from natural resources through extraction. And then we hope that our products degrade back into innocuous natural resources again, if things were perfect. And this is the regeneration system. And nature is filled with examples: termites on termite mounds, dung beetles, bees having pollen, lions eating prey. The human-built world, we've got some regenerative packaging. Surprising, a lot of the food system is not as regenerative as you might think. Some textiles and some things, but we've just started scratching at the surface in the human-built world to do this. And I would argue that's because we have not figured out the materials metabolism yet. And then finally, the last thing is we want to have our stable ecosystems, okay, in which, we all have in our mind what that means. So if we put this whole thing together, all right, we see that we have these 5 things, and it's not a circle, it's not a loop, it's a pendulum. All right, and that's really important, that the human-built world goes clockwise and the natural world goes counterclockwise. And essentially the human-built world and the natural world, as this circular pendulum comes into proximity, it is actually that overlap that is most important, because that, in my opinion, is the definition of sustainability, is how porous, how much overlap does that interface have? It is hubris of us to believe that humans ever going to do anything that has no impact on human health and the environment. It's always going to have some, but we need to consciously understand that and mitigate it and keep it as small as possible. And for me, that is an algorithmical way of assessing sustainability in any system. But one of the things here about this map, okay, is I'm a full member of the Club of Rome. This is the people that backed Donella Meadows back in the 70s, systems thinking. We have to apply a great deal of humility when we map things, because no one is smart enough to get everything perfectly right. And it's not often the things that you put in the wrong place on a map that comes to get you. It's the things you forget. Okay, when we recycle, when we mechanically recycle and manufacture stuff, there is inevitably leakage. We didn't put it on the map, but stuff comes out of that loop. And when that stuff comes out of that loop, what happens is a little bit of porosity gets introduced between the human-built world and the natural world, and we lose a little bit of sustainability. When we synthesize and reprocess materials, there's leakage, stuff comes out, and that stuff ends up creating some porosity between the human-built world and the natural world, and we lose a little more sustainability. When we extract and degrade this leakage, we get more porosity, we lose more sustainability. So it's not just the stuff on the map, but it's the stuff coming out of the map that we have to worry about, right? Because when you think about it, anyone who puts together a map, oh, this is how I'm gonna control all my materials flow. You don't see this put on many maps. You don't see this put on any maps. You don't see this put on any maps. You don't see this put on any maps. And so the stuff that we don't anticipate, the leakage, ends up oftentimes being part of the biggest problems. But if we're not mapping and recognizing that and looking at boundary conditions, we mess up all the time. And so when I look at the system, going clockwise, we can talk about behavior. We can work with, populations and people and help invent technologies that allow them to adopt a more sustainable lifestyle. Again, from the space station perspective, that's just a must do. Unfortunately, the rest of the billions of people on planet Earth don't have any imposition to this, and so we need to invent the technologies to facilitate that. Now, going counterclockwise, we need to invent technologies that are actually, in fact, more compatible with sustainability in nature. And so it's not one or the other. Yes, there are behavioral things that we need to invent technologies to help. And yes, there are technologies that need to be invented that on their own are inherently more sustainable. Okay, and why I love the materials metabolism section of this diagram is because we have the most design degrees of freedom. And so this is where it's mostly our opportunity is greatest. And that is the field of green chemistry. I'm not going to go on to this. This is my life's work. I published this book back in 1998 with Paul Anastas. We started talking about this and working on this in 1990, 1991. Love to come and talk to you more about green chemistry specifically, because I feel that is an amazing opportunity. But right now, green chemistry is just what are the principles that you need to apply when you're inventing a new material to anticipate these things. Because the bottom line is if you look at every chemistry program in the country, in the world, very few, if any, train scientists to anticipate negative impacts on human health and the environment. And if we don't have that training, how can we invent the things? And so of all the products and processes that we have available today, I would argue maybe 10% are truly sustainable, truly benign. 90% of them have somebody shaking their fist. Now, sometimes this is real serious and sometimes maybe not so, but there's a lot of problems. I'd say about 90%. If you do a Google search and look for some alternative that might be acceptable, maybe you might find 25% of the time something. But right now, I would argue in 2022, more than 65% of the truly sustainable solutions have been invented yet. So my definition of green chemistry is a technology that works better than an incumbent technology, costs better than an incumbent technology, and oh, by the way, is better for human health and the environment. If the technology doesn't work, if the technology is too expensive, we're not going to solve world problems anyways. So for me, when I say 65 to 70%, when I'm talking about the technology that works better, costs better, and oh, by the way, hit sustainability targets. If you accept that definition, then really the only barrier for green chemistry and sustainability is invention. And so from my perspective, sustainability is in an innovation crisis. We need to invent technologies to allow us to be sustainable. And I got to ask ourselves, do we have the tools and the skills to do that? That's why it's so important to me that NASA and the space station, help get involved in this, because this is where innovation is desperately needed. It's a benefit. It's a win-win all around. Okay, so the thing is that we talk about loops. Okay, the circular economy, circular loops, closed loops, natural resources, manufacturing, distribution, use, collection, and we talk about a closed loop, and that's a very important thing. But also the very language of closed loop. Listen to what we're saying. We're not only talking about keeping things in, but we also could inadvertently be keeping things out. So if we don't focus on this correctly and we try to define our systems based on the technologies that exist today and don't anticipate technologies of the future, this closed loop could also prevent invention from getting in. And so that's a scary thing for me. If we overly focus on defining our systems today, we don't know what the future, the unknown, what we could do tomorrow. So I look at it with a little bit of a twist, and I say there's the materials ecology, which I described here, and there's also the intellectual ecology of basic research, applied research, development, scale up, commercialization. And using this Mobius strip metaphor here, what I'm saying is that the human-built world of natural resources and manufacturing and the intellectual world of innovation, creativity, they can't be separate. We can't be looking at spokes and wheels. We really have to look at this as an intimate relationship between industry, innovation, creativity, and science and technology and academia. And again, what better place, in my opinion, to be talking about this than on the space station in NASA? Because now here we are, it's 2022. There are factories in South America and North America and Europe and Asia. There's the electronics industry, the pharmaceutical industry, the cosmetic industry, the textile industry. And here we are trying to weave some logical thing to make it all work, to have it all fit together. But you know what? These things were invented like 30, 40, 50 years ago. We're not inventing things to be sustainable. We're trying to invent technologies to bring together things that were invented in an entirely different world with a different mindset. So yes, we have to focus on the existing materials, but where the true sustainability is coming from is not from pushing things together from the past, but inventing things in the future. Because you know what, when I look at all these things, the different industries and the different types of factories, I don't see them all being different. I actually see them all speaking the same language. Chemistry and biology, those rules, that language is all part of this. And so if we can rethink about innovation, creativity, learning from nature, and doing high-tech new inventions with new materials, we and everyone else can literally imagine seriously a truly sustainable future. Thank you very much for giving me this opportunity. And I hope that we have a lot of opportunities to continue this conversation in the future. Thank you.